Good morning and welcome to MAE 106, Discrete Mathematics with Probability. My name is Richard Gohar and this is Lecture 10, Fallacies. Hopefully everyone can hear me okay. It's always good to have a thumbs up in the chat. Make sure that everything is working okay. Okay, perfect. So, what we're going to look at today is fallacies. Fallacies coming from the word in Latin fallo, or fallo, meaning I deceive. And in particular, we're going to be looking at formal fallacies, and these ones we'll call non sequestors. And again, it's coming from Latin for does not follow. So there's kind of three main classical non sequestors. So the first one is called Affirming the Disjunct. Okay. So it comes with the major premise being P or Q, and then we affirm one of the disjuncts. So in this case, we'll say P. Therefore, because of one of these being selected, it's not Q. So here's my premises. And there is the conclusion. And the issue or the fallacy that's cropping up is that the person who is making this argument is confusing the disjunctive, so they're confusing the kind of regular disjunct that we use with the exclusive disjunct. Remember when we had P and Q, the exclusive disjunct was when only one proposition was true. Whereas if we just have the regular old disjunct like this one, again, different. So just because we affirm one event doesn't mean it disqualifies the other proposition. So what we can do is we can show this is a fallacy by using a truth table. So the way that we would do this is we'll construct our truth table, P, Q, then we can look at our premises. We have P or Q. We have P, that's our premise. And then we'll write not Q. I was just, yeah, I know that we wrote that over here, but maybe just to keep this consistent. So we have our two prime propositions, P and Q. I'll just copy this over here. And flipping the column here. And okay. So here are our premises that we had. Here's our conclusion. So what we'll do is we don't really look at the prime propositions. We're looking at the premises, and we go through it every time when all of the premises are true. The conclusion should be true if it's a valid argument. So we'll kind of go through. We see here right on the first line, we have it fail. I know when you look down here, true, 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 that's good. But because it does not always give us a true conclusion, when we have true premises, it's invalid or it's a fallacy. So since it fails to have a true conclusion, every time there are all true premises, it is not valid. Therefore, it's a fallacy. And I think before I go further, did everyone get the same truth table that I have right here? Okay, good. So confusing the V with the disjunctive, the exclusive disjunct is what was causing this issue. So that's kind of, let's just say that this is the end of, let's say that's the end of this example, or this example of a non sequester. You know, in math, we're always kind of, I know it may sound odd, but there is a playfulness to math. And so the question now I'm thinking is, could we have fixed this to have somehow made this valid? So could this be valid if, so instead of doing the just regular disjunctive, if we use the exclusive, then we did P, therefore not Q. And so we can just write out our truth table, PQ. We wouldn't use the exclusive. Then we would have P and not Q. So again, it's only when one of them is true. Copy this column again. We'll flip the Q. Now, what we'll do to check, we'll go through again. Here are the premises. There's the conclusion. And so we can just go through looking for when the premises are both true. And this is the only case, and it is generating a true conclusion. So this is a valid argument. Okay. So that's how we could fix it. Okay. So before I go to the next one, let's make sure that everyone has common terminology. So we have that's read as if P then Q, and here in English we usually call this the antecedent. And over on this side, this is called the consequent. So why is this important? It's because we're going to do number 2 for the non-sequester, and that's affirming the consequent. It's also known as the converse fallacy. So what we do is, to make this fallacy, we start out with the implication P implies Q. And not like modus ponens, where it would say P, instead they assert that Q is true. Okay? So therefore, P. So what they are doing is they're asserting that Q, or the consequent, is true. So that's why we call it that. And like we said, we can have cause and effect. Just because that you have a effect showing up doesn't mean that it's necessarily true that it's the cause is your conclusion. What I mean by that is, if we have an example, okay, let's assume that this is true. So if I have COVID, then I'll have a fever. So we'll call that P, and this will be Q. So just assume that's true. It's not always the case. But let's assume that this is true. Then we'll assert or affirm the consequent, which is I have a fever. Here's Q. Therefore, I have COVID. And this is a fallacy. The reason for that is because, again, just because you have an effect show up doesn't mean that you have the cause. And of course, I'll just kind of put a little time in to end that example. If I do PQ, let's do, okay, so we'll do our premise. We'll have our P implies Q, Q, P. So again, we're looking at the premise right there, and here's our conclusion. So same thing, we'll just look through where we have, okay, so there's true and true, and that generates true. But we have the one case where the conclusion's not true when all the premises are not true, so it's a invalid or not valid. Okay. So we're thinking of like cause and effect, or let's do another example. So affirming the consequent. So let's say if I'm in Kingston, then I'm in Ontario. Again, that's true. Oh, so if the premise is both true but the conclusion is false, it's a fallacy. Yes, that's correct. So you only have to have one case where it fails, where it becomes no longer a valid argument. So you just need one for it to fail as valid. Okay. So if I'm in Kingston, then I'm in Ontario. This is true. Then the next one is, I would say, I'm in Ontario. So I'm in Ontario. Therefore, using this fallacy, therefore, I'm in Kingston. And that's not true. I mean, there's lots of other that's not necessarily true. I could be, well, with the magic of the internet, I could be broadcasting this anywhere. I could be, I could be in Ottawa. I could be in Toronto. There's Thunder Bay. The list goes on. There's lots of cities in Ontario. But that's the problem with fallacious arguments, that these could be true, but then they generate conclusions that might not be true. In fact, I am in Kingston, but this is not necessarily true. And that's the problem with fallacies, is that you could be passing in true things into it, and you can't be sure of what the conclusion is anymore. You can't be sure that it's true. So that's why we have to be very careful. And so it's not necessarily the premises themselves that are causing the problems. It's the way that we have connected these propositions together that is causing our issues. So it's in the structure of the argument, not necessarily the propositions themselves. Okay. That one. Correlation versus causality. That is a matter for statistics. So we have denying the antecedent. Okay, so we had done affirming the consequent. So it's the first one, right? The affirming the consequent, which is the second one right here. So that's what we did here. In this one, we're going to be denying the antecedent, which means that we're going to say that this is not true, the first part. So we start with the implication. So we say something like P implies Q. Then we deny the antecedent, which is P. Therefore, they say that it's not Q. Oops, I didn't mean to knock the microphone there. So, you could have, here's our example. Let's do with the COVID one. Let's say, let's use that same implication if I have COVID. If I have COVID, then I'll have a fever. Okay. Then the next one we'll say, so that's the implication that we're given. We'll assume that this is true. Then we'll say that I don't have COVID. So I don't have COVID. So that's a not P. So therefore, I don't have a fever. Okay. And I can tell you that I don't have COVID, but I do have a fever at the moment because I have a headache. Not everything is caused by that. So again, you could have a true premise. So you've made this cause and effect, that there's COVID-19, then you'll have a fever. This can be true. I don't have COVID, but then the conclusion is not necessarily true. I don't have a fever. And in fact, you could have a different virus. You could have a headache. Lots of other causes for that. So again, it's denying the antecedent is a form of a fallacy. It's also thought of as the inverse error, and the reason for that is when we were talking about the converse fallacy, they're thinking of P implies Q. You know, this would have been fine if we had been working with this implication. You know, if I was working over here and I was given this, the Q implies P, and then we did Q, therefore P, well, this is an example of modus ponens, right? It's written in a different way because we're used to seeing it as P implies Q. We have the antecedent, therefore the consequent, but we've just kind of changed the order. It's okay. That's modus ponens. But the order does matter in which this happens. And so that's why they'll call it the converse fallacy. Somebody has made a mistake thinking that it's Q implies P, and that's not the case. And the same thing happens over here, is the error of the inverse. The inverse is P implies not Q. You know, again, if we were given not P implies not Q, not P, therefore not Q, this would have been fine, because again, this is modus ponens. Again, it might have been written a different way than what we're used to seeing. But still, you have the antecedent being affirmed and the consequent is your conclusion. But that's not the case that they have right there. Because again, the order does matter. P implies Q. So that's a fallacy. Let's just do one more example. let's say I mean what I say. So we'll kind of say that this is kind of P, here's Q. I didn't mean it. Let's say that that's not P. So if I didn't mean it, I mean what I say, I didn't mean it, therefore, the not Q would say, therefore, I didn't say it. And again, same thing. That's not necessarily true. You can say it even though you didn't mean it. And we can do a truth table as well for this, just using our so P, Q. So here's our premise. P implies Q. Then we'll have not P is our second, or the minor premise, and our conclusion is not Q. And just filling in the table. And hopefully you got the same one that I did. Okay, and let's look through here. So we look for the premises where they're both true. And it fails. So conclusion not true when all premises are true. Therefore, it's a fallacy. Okay, so now that we've gone through the three types of non-sequester, let's do an example or an exercise. Let's call it an exercise then. So here's an argument. Let's do coffee is energy. Okay. What else? Kerosene is energy. Therefore, kerosene is, let's say, coffee. So, well, let's C be coffee, E be energy, and we'll use K as kerosene. What we'll do is we'll convert this to a symbolic form. So symbolically, the first premise would be, we'll do coffee implies energy, kerosene implies energy, therefore kerosene is coffee. And this is just not true. There's no link. You can be thinking of it as we have energy. So we said that coffee is energy. We have kerosene as energy. But there is no link. You cannot just draw an implication from K to C this way. It's just in the way that we have structured this argument, you can't assert this. So you can already you have your feeling that this is probably not going to be a valid argument. So to test this, we'll write out we'll have C, we'll do E and K. Those are our three prime propositions. We'll do C implies E, that's our first premise. We'll do K implies E as our second premise. And then therefore K implies C. Keep us, okay, there we go, as much as I can on the page there. So we're just kind of filling in the truth table for this. And now we need to do our correct column, so we'll be going from C to E. Right, coffee to implies energy. So this is true, true, false, false, true, 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 true. Now we'll be going from kerosene is energy, so from this column to this column. So true implies true, that's true, false implies true, good. And we just keep working down the column. Okay, and lastly, we do K to C, so it's from this column to this one. And hopefully you're all checking, make sure that I'm doing this correctly, that you're getting the same values I am. From K to C, so true, true implies true. It may be tedious, but take your time. You don't want to make a mistake. Because one little error and you will get the wrong conclusion about your argument. So So let me just double check this again. So from K to C. Okay. Yeah, the Peter fallacy. So here's our premises. Here's our conclusion. And I'll pull out this highlighter. And we'll just work through here. So there's true and true. That's good. Good. Okay. But again, it just takes one case. And so if you are kind of looking to see if this is a fallacy, again, I'll just check these again. So C to E, so that's true. K to E, that's true. And then K to C, that's false. So therefore, it's invalid / a fallacy. Number 5. So let's do another exercise. Is this valid? So we can look at P implies Q. Q implies R. So, in this argument, we'll have 3 premises. We still have one conclusion. Now, okay. So we can quickly check this using a truth table. We have P, Q, and R. So we'll do P implies Q. Q implies R, not P. again, we're just doing our implication table. When we do Q implies R. And lastly, I'll just flip this column here. So okay, so again, hopefully everyone's checking my truth tables. Here are the premises. Here's the conclusion. And we just go through and look for when we have all true premises. So that's the only case, and it generated a true conclusion. So therefore it's valid. But I kind of knew that this was a valid argument before I even started. And the reason for that is because I can see the hypothetical syllogism. So we had the P implies Q, Q implies R. So therefore, I knew from the hypothetical syllogism that P implies R. So using that, I knew, so I had P implies R. Then I had not R, therefore not P, which we know is true, or this is a, so this is the hypothetical. Did I forget how to spell it? Hypothetical, like that. Syllogism. Then over here, this is modus tollens. And so I have, this is a valid argument, so I knew that this conclusion is from P implies Q to Q implies R, that I had, this was going to be a true. I passed this into modus tollens. Again, this is true, and I would be generating a true conclusion as well. So I also knew that this is valid as well. So the idea is that if you're passing one valid argument into another, it's okay. Because again, you're generating, if these are true, this will be true as well. That's getting passed in. And this argument will be generating a true conclusion as well. So we're safe. But this was just when I saw that, that's how I could quickly determine that this was valid. I didn't have to actually use a truth table. We could just see that quickly. So that's kind of the reason why we'll have some of these formal ways of describing arguments. Yes. Because maybe you might not have time to quickly write out a truth table when you're sitting in a meeting, but you can quickly write out something like this, and you can already quickly see that it's valid. Okay. Thank you everyone for tuning in. I'll see you on Friday. If there's any more questions, feel free to send me an email. I also have office hours tonight. There's provided in the Zoom link through Moodle, and there's additional hours on Friday evening as well. If you're not able to make it tonight, if there's no more further questions, I'll sign off for today and enjoy the rest of your afternoon. Have a good day.